Good morning and welcome again. Let's graduate now from curve modeling and move on to the third column of our layout and start with discussions on surface patches. Before I do that, let me put things in perspective. So we have this typical solid here, and we have based our course on the extended Jordan curve theorem, which says that a simple closed and orientable surface bounds a solid. You can divide this bounding surface into a set of patches, each of which will have curved boundaries, and each of the curve would have its respective endpoints. We have devoted a lot of time on solid modeling and different methods on curve modeling. A quick recap: in solid modeling, we discussed topology. We discussed three different methods of solid modeling, namely the wireframe approach, the BREP or the boundary representation method, and constructive solid geometry. In curve modeling, we discussed primarily three models. Those are the Ferguson curves or segments, Bezier segments and curves, and more importantly, B-spline models. We devoted quite a bit of time on B-spline segments. It's time for us to move on to surface patch modeling. This is lecture number 33. We start with differential geometry of surfaces. Before we start, what would be our objectives? We know that a solid can be modeled by a simple closed and orientable bounding surface. The closed surface is a result of different non-self-intersecting patches knit at their common boundaries. Like for junction points of curve segments, we need to address the continuity conditions at common junction curves of different patches. What do I mean here? Well, let's take a look at this solid. Each of these are surface patches, and these are curves which are common between different surface patches. For example, this curve or this segment here is common between these two patches. We need to worry about the continuity between these two patches around this curve. By around, I mean both along, like so, and across, like so. And for that, we need to study different differential properties of surface patches. We'll start with some of them today. Let's first try to understand how we can mathematically represent a surface patch. If you recall, we have been working with parametric equations. A curve segment, as you would know, is represented using a single parameter. But a surface patch needs to be represented using two parameters, u and v. This is a typical surface patch. You can draw a set of curves on this patch, for example. If you think about it, will have 4 bounding curves. Along 2 curves, one can think of using the parameter u, and along the 2 other curves, this one and this one can think of using the parameter v. So if we take a look at this curve, we can think of parameter u as being constant. Likewise, along this curve, parameter v is constant. This point here is an intersection between these 2 segments, and it's represented as r of u sub 0, v sub 0. So along this curve, u is, say, u sub 0, and along this curve, v is, let's say, v sub 0. You can think of constructing tangents along these 2 curves. At this point, along this curve, let's say we have this tangent represented by r sub v, because it's along the v direction. Likewise, we can have a tangent along this curve at this point represented by r sub u, which is along the u direction. The parametric equation of the surface patch can be written as r as a function of u and v, which is the scalar field x, function of u and v, times I, plus scalar field y of u and v times j, plus the third scalar field z in terms of u and v times k. These are unit vectors along 3 mutually orthogonal Cartesian directions. So this scalar field will represent the x coordinate of a point on the patch. This would represent the y coordinate, and this would represent the z coordinate on the patch. Let's take a look at some analytical surfaces. An xy plane. Its parametric representation in Cartesian form is r of u and v, which is equal to u times I plus v times j. And in polar form, a plane patch r u of v can be written as u times cosine of v times I plus u times sine of v times j. A sphere, for example, another analytical surface, can be expressed in terms of parameters u and v as r of u and v, and that's equal to a times cosine of u times cosine of v times I plus a times sine of u times cosine of v times j plus a times sine of v times k. Here a is another parameter. This is how a sphere looks, you know that. As the third example, we have a catenoid, which can be constructed via the rotation of a catenary, which is given by y equals a hyperbolic cosine of x over a, and the rotation is about its directrix, say the x-axis. This is how a catenoid would look like, whose equation in parametric form is given by r of u and v equals u times I plus a hyperbolic cosine of u over a times cosine of v times j plus a times hyperbolic cosine of u over a times sine v times k. Likewise, you can construct many other parametric forms of different surface patches, whether analytic or freeform. Let's try to understand some concepts now pertaining to surface patches. Simple sheet and an ordinary surface. So what's a simple sheet? A simple sheet is continuous and obtained from a rectangle by stretching, squeezing, and bending, but without tearing or gluing. So these are some topological operations that we had studied way back while discussing solid modeling. A cylinder will not be a simple sheet. Why is that so? Because we'll have to cut it to be able to get a rectangle. Likewise, a sphere and a cone are not simple sheets because there are cutting operations involved. A flat sheet with an annular hole is also not a simple sheet. If for all points P on the surface, a portion of the surface containing P can be cut, and if that portion is a simple surface, then the entire surface is termed as an ordinary surface. So let's say we have this arbitrary surface here. It can have any shape. This surface is constituted by a set of points P. Let me take any portion of the surface and cut it. So this is the portion I have now, and I realize that this portion is homeomorphic to a rectangle. In other words, I can perform any topologically permissible operations on the rectangle to get the shape. Since this is homeomorphic to a rectangle, I would say this is a simple sheet. And if I can perform this operation for any portion of such a surface, then I would say that this surface is an ordinary surface. Let's take a look at some singular points and regular surfaces. Let R sub u and R sub v be derivatives along u and v at the point R, u sub 0, v sub 0 on the surface. So we have the surface patch, we have the parametric directions identified u and v, we have the curves corresponding to the constant parameter value u and the constant parameter value v. These intersect at R of u sub 0, v sub 0, and we have at this point tangents R sub u, R sub v. So this point R u0, v0 is a regular point if these conditions are satisfied. R sub u is given by partial R over partial u evaluated at u sub 0, v sub 0. R of v is given by partial of r over partial of v, again evaluated at u sub 0, v sub 0, and the cross product between these two directions is not equal to 0. Once again, what we are saying is that point r u sub 0, v sub 0 will be a regular point if these directions exist mathematically, and that the cross product between these two tangents is not equal to 0. This is what I said just now. The slopes r sub u and r sub v should both exist at a regular point, and that the cross product between these slopes should not be 0. A surface patch will be a regular surface patch if all points on it are regular points. One would get a singular point if either of the three conditions doesn't hold. That is, if either the cross product is 0 or any of the slopes Ru and Rv are either undefined, they may not be unique, or they may not exist, or any of these directions is 0, or they are coincident. If x sub u is given by partial x over partial u, x here is a scalar field in parameters u and v, giving the x coordinate of the parametric surface patch. If xv is defined as partial x over partial v, likewise for the y coordinate of the patch, if yu is defined as partial y over partial u, if yv is defined as partial y over partial v, and if zu as partial z over partial u, and zv as partial z over partial v, then one can compute the cross product between the two tangents r sub u and r sub v. You would know that the cross product is given by the determinant of this 3 by 3 matrix. The first row contains the x, y, and z direction unit vectors. The second row will contain x sub u, y sub u, and z sub u. And the third row will have x sub v, yv, and zv. And for the cross product to be not 0, this is what the condition is. One can compute the three Jacobians for this determinant. The first one is the determinant of this 2 by 2 submatrix, xu, yu, xv, yv, represented by j sub 1. The second Jacobian, j2, is yu, zu, yv, zv, the determinant of this 2 by 2 matrix, which is this one here. Likewise, the third Jacobian, j3, is given by the determinant of the 2 by 2 submatrix defined by these columns, zu, zv, xu and xv. So for this cross product to be not 0, at least one of the Jacobians, J1, J2 or J3 should be non-zero. Let's look at some examples where we see singular points. This is the first one. The patch is a self-intersecting patch that looks like this. Try to identify the two parametric directions. I'll possibly use the parametric direction u like this. Once again, like this. And the parametric direction v will be along this intersection line. Let's consider any of the points on this region here, on this line. So at this point, if you think about it, we'll have two directions pertaining to the tangents along the u direction. One will be given by this here, r of u, and the other will be given by this, r of u. There would be a unique tangent along the v direction, r of v. So since the tangent along the u direction is not unique at this point, we would say that this point is a singular point. It's not a regular point. The second example, it's a patch that looks like this. So let's say this is a curve along the parameter u, and the vertical curves would correspond to parameter v. What do you have to say about the points on this edge or along this edge? Something very similar. If you look at this point, you will have non-unique tangents along the u direction. So you'll have multiple directions pertaining to r sub u, while you'll have a unique direction pertaining to r sub v. Once again, one of the tangents is non-unique, and therefore all the points on this edge are singular points. This one is the third example. If you look at this point here, or maybe this point here, this is a singular point again, because tangents are not uniquely defined. All other points on this patch in this figure, on this one in this figure, and here are all regular points, because the three conditions that we had seen before are satisfied. Let's look at the tangent plane and the normal vector now. We have seen this figure before. Let's try to concentrate in this region. This is a point of intersection between two parametric curves, u equals u0 and v equals v0. We have the tangents Ru and Rv defined. This plane here that contains the two tangent vectors is called the tangent plane. The unit normal, small n, or the normal, capital N, as a function of u and v is given by the cross product of these two vectors, r sub u and r sub v. Both are functions of parameters u and v. Of course, the unit normal will be this cross product divided by its magnitude. At a regular point, the normal to the surface is well defined. Let's see what happens for surface patches given in implicit form. In other words, for equations f of x, y, and z equals 0. The normal direction is given by partial f over partial x times I plus partial f over partial y times j plus partial f over partial z times k. And the unit normal, small n, is then capital N divided by its magnitude. You would want to ask, or maybe you would know already, as to why the normal for implicit surface patches is given in this form. Let me work out the answer to this question for you on board. Say we have this implicit surface patch, and the position vector of any point on this patch is given by r equals x uv I plus y uv j plus z uv k. That means the x, y, and z coordinates of this point are functions of parameters u and v. Let's differentiate this function with respect to u. We'll use the chain rule to get partial f over partial x, partial x over partial u plus partial f over partial y over partial u plus partial f over partial z over partial u, and this is equal to 0. Differentiation of 0 with respect to u is 0. Likewise, let's differentiate this equation with respect to the second parameter, v. Partial f over partial x over partial v plus partial f over partial y over partial v plus partial f over partial z over partial v is also equal to 0. Now let's try to express the two left-hand sides in a slightly different form as a dot product between two vectors. So these are equations A and B. So I can write equation A as partial f over partial x I plus partial f over partial y unit vector j plus partial f over partial z unit vector k dotted with partial x over partial u I plus partial y over partial u j plus partial z over partial u unit vector k. And this is equal to 0. Likewise, equation B is partial f over partial x I plus partial f over partial y j plus partial f over partial z k dotted with partial x over partial v I plus partial y over partial v j plus partial z over partial v k, and this is again equal to 0. Now try to identify what this vector is. This is the tangent along the u direction. How about this one? This is the tangent along the v direction. So what are these two equations conveying? They are conveying that this vector is orthogonal to r sub u, the tangent along the u direction, because of this condition, and the same vector is also orthogonal to the tangent along the v direction. Since Ru and Rv constitute the tangent plane, this vector is orthogonal to the tangent plane, and therefore it has to be normal to the surface at point R, U, V. So this vector here aligns with the normal vector. The tangent plane is a plane containing the tangent vectors r sub u, function of u and v, and r sub v, which is also a function of u and v, at some point p for parameter values u sub 0 and v sub 0. In Cartesian coordinates, this point is expressed as x sub 0, y sub 0, and z sub 0. Now, for a point, as a matter of fact, for any point q, which is given by x, y, and z on the tangent plane, let's say we have the free vector given by pq, which is equal to x minus x0 times the unit vector I plus y minus y0 times j plus z minus z0 times k. So for q to be lying on a tangent plane, this vector on the tangent plane must be perpendicular or orthogonal to this normal here. In other words, PQ dotted with n must be equal to 0. And this would give us the equation of the tangent plane. So I have copied the previous condition here. If the normal is given by the cross product between two vectors identifying the tangent plane, namely RU and RV, and if we can extract the unit normal from this information, then we have PQ dotted with RU crossed with RV, which is given by the determinant of this 3 by 3 matrix. Now this here is a scalar triple product with elements x minus x0, y minus y0, z minus z0. In the second row, we have partial derivative of x with respect to u, y sub u, z sub u, partial derivative of x with respect to v, the same for y, and the same for z. And because of this condition, it's equal to 0. As I said, this would give us the equation of a tangent plane. In case our surface patch is expressed in the implicit form, f of x, y, and z is equal to 0, then we'll have a slightly different equation. Then our normal is given by the gradient of this function, partial f over partial x times I plus partial f over partial y times j plus partial f over partial z times k. And we know how to compute the unit normal. For this case, the equation of the tangent plane will be given by the dot product between PQ and the gradient. That is x minus x0 times partial f over partial x plus y minus y0 times partial f over partial y plus z minus z0 times partial f over partial z equals 0. Let's work an example on the board for the case of a spherical patch. So the patch R as a function of two parameters u and v is given by A cosine of u times cosine of v times I plus A sine of u cosine of v times j plus A sine of v times k. So this is x uv. This is the scalar field y uv, and this one here is z uv. Let's compute the tangent at any point. So Ru of uv, the tangent along the u direction, is partial r over partial u. In ordered form, this is given by x sub u, y sub u, and z sub u. Partial derivative of x with respect to u, partial derivative of y with respect to u, and partial derivative of z with respect to u. So x sub u is minus A sine u cos v. Y sub u is a cosine u cosine v. Z sub u, there is no u dependence here, so this is 0. Likewise, the tangent along the v direction is given by r sub v uv. This is partial r over partial v. In ordered form, this is x v, y v, z v. So x of v equals minus a sine u sine of v y of v equals, this should be cosine of u, y of v equals a sine u sine v with a negative sign, and z of v equals a cosine v. So let's compute these two tangents at a point on the sphere. Let's say for u equals 0 and v equals 0, what do we have? So r for 0, 0 equals a, this would be 0 and this would be 0. This is a very simple example. Let's continue with it. So r sub u, the tangent along the u direction at 0, 0 will be this would be 0, y of u will be a, and z of u will be 0. Likewise, the tangent along the v direction equals x of v is 0, y of v will be again 0, and z of v will be a. Let's get some geometric perspective here. So this would be the portion of the sphere, and it is at this point a 0, 0 that we are trying to compute the two tangents. The first tangent r of u here will be along the y direction, 0, a 0. This is r u. The second tangent r of v will be along the z direction, r of v. Clearly, the tangent plane will be the y-z plane geometrically. Say this is our tangent plane, and let's have a point P here given by x, y, z. Let's say this is point O here, where we have defined our two tangents. And the coordinates of O are given by r, 0, 0. So the equation or the free vector OP is given as x minus a I plus y minus 0 j plus z minus 0 k. I can compute the cross product between these two tangents, RU and RV. So the normal n is RU crossed with RV. This is given by the determinant I, j, k, 0, a, 0, components of RU, and 0, 0, a, components of RV. This is I times a squared minus j times, this would be 0, minus k times, this would be 0 again. So this is equal to a squared times I. And since OP is perpendicular to n, we have the condition OP dotted with n equals 0. This would imply that x minus a I dotted with a squared I is 0. This gives x minus a equals 0, or x equals a. Now if you realize, this is the yz plane intersecting the x-axis at x equals a, which is what we expected. This is a very simple example, geometrically insightful, that allows us to see how we can compute the equation of a tangent plane. You can expect many more complex examples in real life.